So last time on PNGE110, only the finest in petroleum statistics classes you have on Tuesdays from 3 to 3:50 p.m. We talked about sampling from a triangular distribution. So it's your values axis, it's your probability density axis. This point in the center is what? Your mode. This is max. This is min. This is the probability density of the mode, which is defined to be 2 over max of your data minus the min of your data. Cool. And that defines our triangular distribution. One of the nice things about this, as opposed to creating like a joint probability table, is that it's a continuous distribution. It's not discrete. So I can look literally for any value and get a probability density associated with it. I can look at any value between the maximum and minimum, and I can get a probability here for it. As opposed to, like, say, your joint probability table, you're restricted to whatever your bin size is. So it's a little bit more restrictive, especially when you don't have a lot of data. So that's kind of the advantage of a continuous probability distribution, right? And last week we talked about sampling this, so you're able to pull, saying, okay, I've defined this based on some data set. Now I can pull numbers out of it that correspond with this distribution that my data might have or appears to have. I can start doing statistical tests and analyses and make predictions and all that fun stuff that makes life good. So when we start to pull these, when you start to pull data and form this distribution, the SP is kind of defined some terms for how likely different things are. So they define it by this resource classification system. This is from a 2000 year from a document published in the year 2000-ish. I know, ancient history and all that jazz, but it's still there. But it's still their standard. So what we're looking at is up here. So whatever is defined as reserves. Reserves being defined as, gosh, I'm forgetting right now. Nomenclature. There we go. Reserves are commercializable petroleum products. So these estimates are focusing on stuff that we can use. It's stuff that's worth going after. You can kind of infer that too from the different categories he's here for the different kinds of projects. You either have something that's presently producing, is being developed, or that could be considered for possible development in the future. So how these reserves get categorized are into these kind of odd sounding buckets. You either have reserves that are proved to be there, you have reserves that are probably there, and reserves that are possibly there. And those mean something very specific when you start talking about them quantitatively. So, proved, probable, and possible. You'll also see these referred to as P10, P50, and P90 as estimates. These all correspond to probabilities of exceedance. Okay. So what a probability of exceedance means is that for for P10, how do I want to say it? How do I want to say this? Did I just write this backwards? Oops. Yeah. Okay. I wrote that. Sorry, I wrote this. Sorry, I wrote this backwards. I knew there was something strange there. Proved is P90, probable is P50, possible is P10. Sorry. What this means is that for P90, it means that 90% of the estimates that show 90% of what you might encounter here down there will exceed whatever the P90 estimate is. So if you have an estimate for, say, like the original oil in place, there's a 90% chance that you will exceed that estimate in terms of what you actually get out. Write that out. 90% of estimates will exceed. Or you will definitely get at least this. You will recover at least this from the reservoir. That's P90. That's why it's considered proved, because there's a very high chance that it's going to occur. You might also see this noted as a 1P estimate. The next bucket would be a P50 estimate, or the probable. You will also likely see this as median, mean, probable, 2P. It has a whole crap ton of different names. It's not really the mean. It's not really the median. It purely depends on your underlying probability distribution. So it's the P50 estimate or the 2P estimate. What's probably there. So following the same logic, 50% of the estimates will exceed this prediction, or you might say you have a 50% chance of finding down in a reservoir more than the P50 estimate of OIP, or whatever example that you want. Okay? Yeah.
Is that also a 50% chance that you get less than that value?
Yep.
That's a good chance.
It is. Well, at least it was for those who decided to drill on homework too. So the last one, again, the same thing, P10 or 3P PS or 3PS estimate, you have a 10% chance of getting more than this, than the P10 prediction. And so this is the possible estimate. This is the high estimate. This is the high risk estimate. estimate because there's a much lower chance that you're going to get this. So, how would I actually get these things? How do I determine that I will get that I have a 90% chance of getting more than a particular value? How am I going to go about doing that using a triangular distribution? All right, let's have a look. All right, so there's some arbitrary triangular probability distribution. What is the area underneath of the curve?
1.
1. All right. Why is it 1?
That's, yes, probability that you get a value between maximum and
Right. Right. There's a 100% probability that you will get a value between this point, your minimum, and this point, your maximum. 100% chance that that will occur. Therefore, the area underneath of that distribution is 1. So, how would I find the probability of getting between a value between one number and another? Say this value here. Say your min is 500, max is 1,000. We're going to grab 750 ish, 650. This is a little bit more well placed. How would I find the probability of getting a value greater than 650, conceptually speaking?
We just look at the value of 650 and subtract it.
Subtract it from what? And how does this relate to probability?
So what was I saying? Is that right?
You said subtract it from something.
Well, you find it what it is at 650, or given 650 or less.
Say again, please.
You find what it is with, like, getting it within 650.
Okay. What is it?
Probability of getting 650.
How do I find that? How do I find
Just
it?
go up and look at it.
Okay. So remember, this axis is probability density. It's not direct probability. Yeah. Okay. So the same way that the area under the curve is 1. So the area under the curve corresponds to the probability of getting any number any value that is encompassed by the curve. Therefore, area corresponds to probability on a probability density function. So we need to integrate. So if I wanted to find the probability of getting any number less than 650, I'd have to find the area of the curve to the left of 650. That area would correspond to the probability of getting a value from, in this case, 500 to 650. That is 650, I promise. So area corresponds to probability. All right, so let's draw another clean distribution here. Okay, same thing. Your probability density, you have values, max, min. I just drew it connecting with the origin. It does not have to connect with the origin. All right. So now I want to try to develop a P90 estimate. So P90 estimate is what again? Okay, well, it's not necessarily so I have 90% that at least it is there. So what's a way of, so another way of stating that might be, there is a 90% chance I'll find more than that value, more than that value. Is that a fair way to say it? Cool. So if I drew that on a graph, I might say that this area is equal to what? It's not, the area is not equal to P90.
No.
The area is equal to what? For if this value here is the P90 estimate. So if that value waiver right there is the P90 estimate, it's how much whatever I have there or how deep it is or whatever. What is the area that I've kind of sketched out here in orange?
0.9?
Yes, 0.9. Because if areas probability and there's a 90% chance of a value greater than the P90 estimate, that means that the area to the right of it must be 0.9. So if we know the area to the right of it's 0.9, that means we can also back out what the P90 estimate should be. Because by the same token, the area to the left of it should be what? Right. So how do I find area of a triangle? Okay, so area is 1/2 base times height. What's my base here?
Some distance away from the minimum.
It's some distance away from my minimum. It's
What do you want?
that guy right there. Well, you could do the big one too. It just means you have to do more math. So I like doing the small one. So the base would be whatever P90 is minus the min. So the height would be what? Say again?
Something with probability density.
It would be something with probability density. What would be something with probability density?
You have the equation of the line.
Yeah, if I had the equation of the line, that'd be awesome. How do I get the equation of the line?
It's, yeah.
Okay, so that point up there is 2 over max minus min. How does that help us?
So the equation of the line is
So the answer to 0.
probability density equals the slope times x, and it goes through some value that's not the minimum value. Should we assume that the minimum is 0?
It is by definition. I'm sorry. The value of minimum is not necessarily 0, but the probability density is defined as 0 at the minimum and the maximum.
All right.
So that simplifies part of it.
Yep. And that's the equation.
So if you have y equals mx plus b, dy over dx is your slope. So rho m minus 0 over your mode minus min, sweet, times x plus b. Do your substitutions, figure out what all those need to be. But eventually, what you're looking for is a point on that line, in this case right there. And this would be that line, y, evaluated at P9, at P90. So that would give you your height.
So for that probability density, like PMI zero, what if on like the graph it's not exactly at zero, but it's close?
What if it's P90 minus min and min is about 0?
Or what if it's like 0.0005?
Sounds very specific.
Like in the triangular distribution that I made for the homework,
Mm-hmm.
it's like not zero, but it's really small.
Is, Charlie, you mean the actual value for min? Like the actual physical
Probability
value?
density for min.
Probability density of min should be, the probability density of min, of minimum value is defined to be 0. Yeah. So when you make your triangular distribution, you start plotting those points, the minimum value should be plotted at 0. Yeah. Same with the max. Are you saying that because it belonged to a bin that had some probability associated with it? Oh, okay. So the idea with the triangular distribution is that it limits it purposely limits the scope of your problem. Like in a Gaussian distribution, it never touches the horizontal axis. The distribution asymptotes to the axis and goes off to infinity in both directions. Which in one sense makes some sense, because there's a chance you could get a really wacky estimate. There's just a really low chance of that occurring. A triangular distribution is more cut and dry in a sense, because it limits the domain to a finite set of numbers, and it uses the maximum value and the minimum value from the data set that it's formed on as the bounds for that. So probability density is 0 at those extremes. Cool. Or, well, maybe. Anyhow, so we have an expression for area under the curve for that little triangle there, for that little wedge, because we call it the same way that we can say that the probability of exceedance for the P90 estimate is 0.9. You might also say the probability of non-exceedance is 0.1. So we can say that the area of this triangle must be 0.1. From this, can solve a what's going to be a quadratic expression and get what my P90 should be. Cool beans. You can do that same thing for P50 and P10 as well. Those to just be at different points. Might have more or less math to do, but it's all the same. Idea. You're solving for the value that corresponds to these different probabilities, so that you can evolve these kind of industry standard predictions of how confident you can be concerning a particular amount of reserves or other or some other parameter that you want to look at. Okay? Cool. All right. So that's that. Sure I didn't miss anything with that. Yeah, that's all I wanted to do with that. And this does kind of underline, I think, the importance of continuous probability distributions, because you couldn't do that not nearly as neatly or as precisely with a discrete probability distribution. What I mean by that is that if you have a histogram, you're limited by what your bins are. So if you only have so much data, you're probably going to have relatively large bins, which by consequence means that you can't be as detailed in your analyses. The nice thing about continuous distributions like the triangular distribution is that it can create it relatively rapidly and get some kind of first pass estimates. Now, say that I wanted to start putting things together, and this is where the Monte Carlo simulation kind of comes in. I could have some distribution that I figure out from data for, say, reservoir thickness. Then I could have some distribution, say, for porosity. I could have some distribution for, say, formation volume fraction. And, oh yeah, I could have, when I have a fourth one, I could have a fourth distribution that talks about saturation in percentage. So I can form all these distributions based on data that I've acquired through modeling or sampling or whatever. And then like we did this past week, I can sample all of these, so I can get some numbers out. So say one sample is 50 feet, sample that's 0.21. This ends up being some ridiculous number because I'm not thinking of decent formation volume fraction right now. Say again?
I bet it's 50 feet and saw.
Ah, well, it's pretty soft estimate. That and that. So say I sample each one of those once, I get that. In theory, I could I could multiply these together, combine them in some way, right? And they'd give me a prediction for, in this case, original oil in place, right? That'd be like something I could do with this set of data. And then I could sample this again, get another estimate that's a little less soft. It's a little soft, if you will. Get another set of estimates. I can multiply those together. Get another thing of original oil in place. And I could sample these enough times that it starts to that the underlying probability distribution for original oil in place starts to evolve from this data, because it's not. It won't follow this distribution or this distribution, this distribution or this distribution. It'll be some combination of them all. So I can't tell what it is just out of hand. And this is kind of the beauty of Monte Carlo simulations. It's a combination of all these different seemingly stochastic processes, or at least processes I'm modeling as stochastic ones. And it lets and from the probability distribution that I kind of find for some parameter of interest, like OIP, which should be some combination of reservoir thickness, reservoir area, which I didn't sample for some reason, because I should have saturation, porosity, and information volume fraction. I can now see what that looks like, and maybe it looks something like that. I don't know. Oops, like that. And from there, then I now I can start developing my P10, P50, P90 estimates from that. Now this is like a really first pass gig. What doesn't this take into account? What does this sort of analysis miss? How might this be wrong?
In a lot of ways.
Okay, pick your favorite one that doesn't have to do with experimental error.
Different reservoirs,
Okay, what do you mean by that?
like if the oil saturation is for a different reservoir than the other porosity ones, or if it's at a different place in the reservoir.
Okay, so if these are sampled in different locations, is that what you're saying?
Yeah.
Okay, cool. So how do you fix that?
Get someone to do it all at once.
Well, so you're also thinking about changes just in time too. Is that also what you're saying?
Yeah.
Okay, so both things are right, and we're going to deal with them one at a time. So the one point of this was, oh, actually, let's do this, because pretty pictures are worth a lot. Okay. All right, so this is a plot of reservoir thickness from a relatively broad project area. Each one of these squares is about 3 acres-ish. This is from a reservoir model that Dr. Lee was working on last fall. So you can see different well sites and such in this. But the point is that the thickness is spatially distributed. If you just aggregate your samples into some one-dimensional thing, meaning you don't care about when they were gathered, you don't care about where they were gathered, you just care about that they were gathered and they have some correspondence to the area that you're looking at. If you just think of your data in 1D, then right, you miss spatial variations in your different properties, like reservoirs. So you can see that there are substantial variations in this in space. So, kind of the next level of Monte Carlo simulations is not just saying, okay, I have all these probability distributions, but tying down those distributions to a geographic location. So you collect a bunch of data for this point, and 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 this point. And now, well, you can model each area by itself. Going through that same process that we just talked about, but looking at individual geographic locations. One way that you can get data for that is there's starting to be a greater analysis of uncertainties in things like seismic tests. So based on the uncertainties of those results, you can kind of start to create you create probability distributions and model model geographic locations instead of the whole area in aggregate. The next level of this would be what? What are we missing even from this scale of resolution? In what other direction might properties vary? Yeah, depth. So we're also not accounting for vertical heterogeneity as well. And that's also just so variations in depth. So the next level would be to figure out what we call how these different properties vary according to depth as well. Include that into your model analysis, and now you really have a 3D assessment of what's going on underground, and that's really kind of the aim. That's kind of the coup de grace, with the idea being that you can start off, but you find that was a really nice plot. If you find it again, it'd be even better. There you go. You can start off with some sort of 1D analysis, and you'll have a relatively wide range of uncertainty just because we don't know enough. Like I said, you don't have a handle on the geographical variation or the vertical variation in different properties. So your P10, P50, and P90 estimates are going to have a relatively wide spread. And the idea is that as you get more data, as time goes on, you do more work. You'll be able to move from a 1D to a 2D to a 3D model and start to tighten up those estimates and decrease the total uncertainty. And then eventually your statistical model is not going to matter anymore, because you'll have sucked out all of the resources that you care about it. Your knowledge about the reservoir will go to the maximum of its possible extent, be fully characterized, and then eventually you won't need to be there anyhow. So that's kind of the different levels of this modeling brew. Any questions about that? We're probably going to at least just look at 2D things for your project, a 2D Monte Carlo. Definitely not 3D, but probably at least 2D. So, that actually went faster than I thought. That's about all I have for today. Y'all have any questions? All right. Homework will be up soon, and I will see you around.